The National High Magnetic Field Laboratory is a cutting-edge research facility funded by the National Science Foundation. My name's Michael Davidson. I'm a research scientist and associate in research here at Florida State University, assigned to the National High Magnetic Field Laboratory. It's actually a collaboration between Florida State University, the University of Florida, and the Los Alamos National Laboratory. So there's functions of the magnet lab at all three institutions. There's a wide and diverse range of different types of activities going on here at the Mag Lab. I fall into the biological arena. For the most part, my interests are in cell biology. What we spend most of our time doing here in the laboratory is what we call live cell imaging. We're looking at a wide variety of cells, some human, some animal, some cancer, some not cancer. We generally look for cells that are photogenic, regardless of whether there's a lot of biology known about them, simply so that we can more clearly delineate the types of things that are going on in the cells. That's a photograph of an arterial cell from a cow. We use this type of cell as it's a very good model cell because it's spread out sort of like a fried egg, has the nucleus here where the DNA is. It has mitochondria, which are the little powerhouses, the batteries of the cell, if you will. And then the green is the structural component, sort of like the cytoskeleton, the skeleton of the cell. A lot of times this will be one frame out of a video. So we may collect 1,000 video frames that we can play back at 30 frames per second at real time and actually follow this mitochondria as it traverses through the cell. The colors are pseudocolors, but that's the original color that we see through the microscope. These are stained with fluorescent dyes. It's a little fluorescent tag that we can genetically encode. We can shoot the DNA into this cell. The cell itself will start making the green fluorescent protein, and whatever the green fluorescent protein is attached to will show up as a little molecular beacon that we can use to follow it through the cell. We can actually see it moving together and interacting with its partner. Okay, this is one of our live cell imaging laboratories. We have 5 microscopes in here. We keep the lights off so that we don't get any overhead lighting into the microscope lens. The cells are actually right here on the microscope on the top here, so we accumulate a series of images over a period of 4 to 10 hours. We'll see this particular thing here might grow and come back. This membrane here might fold over. These nuclei will move around, but that all occurs over a period of hours. Yeah, we have photographed everything from moon rocks to ice cream and quite a few things in between. The microscope is really a scientific instrument. Most of the things that we do with microscopes are targeted at solving scientific problems. A lot of the things that we photograph are driven by not science but commercialism. So I spent years trying to figure out how to get good photographs of things that normally would be difficult to photograph under the microscope. And I spent probably 10 years of my career studying the crystallization patterns of different chemicals so I could get them to crystallize and photograph. If you do it right, they produce beautiful patterns. In order to get the colors that you see in a lot of our photographs, we use polarized light. And you're familiar with a soap bubble or a film of gasoline on a swimming pool or on the street. You see all those really colorful patterns that arise on that soap bubble because the sun reflects off of it. That's due to interference of light. So when sunlight is a mixture of all wavelengths, all colors, and when it lands on an oil slick and reflects back up into your eyes, certain colors interfere with each other and are destroyed, and other colors you see, like reds and blues and stuff like that. That's the same principle behind the way that we take these photographs. In order to get them to work that way, we have to do a lot of work in order to make the crystals. So with, for instance, beers, you can't just stick a beer in a polarized light microscope on a slide, a drop on a slide, and you won't see anything. So what you have to do is you have to somehow crystallize it. And so what we did was we crystallized the sugars that are in beer, and that took quite a bit of time. In certain cases, in some of the beers, we would prepare maybe as many as 500 to 1,000 different samples of the same beer in order to get one good photograph. So it's a lot of work. As you may know, we licensed images for neckties. We've licensed images to companies that made bed sheets out of them and coffee mugs and calendars. We stumbled across a necktie designer in New York City back in the early 90s. And he was actually making Jerry Garcia custom neckties made from Jerry Garcia's artwork. And I had read in Time magazine that he'd made $35 million with his first year of his Jerry Garcia neckties, so I sent him a whole collection of vitamin photographs. And he calls me up on the phone and says, "Mike, these look neat. Let's make a collection of vitamin neckties." And I said, "That's a great idea. I want," you know, I'm thinking to myself, I want 35 million too, yeah. But they didn't sell that well. We made about 25,000 in royalties. So people just, they're interested in vitamins, but I guess they don't want to wear them around their neck. So we switched gears and we made another collection with photographs of moon rocks. And that was to commemorate the 25th anniversary of Apollo 11 landing on the moon. Unfortunately, the general public does not have an aesthetic appreciation for a photograph of a rock through the microscope, and they really didn't connect on the moon rock necktie, so that was basically a failure. Our third collection was Ben & Jerry's ice cream. I spent 6 months trying to figure out how to photograph ice cream, and it's not easy. It was a real challenge, but I finally managed to get it done. There were about 10 flavors that I did, and they sold like hotcakes. And Erwin Sternberg, the president of that company, called me up one day on the phone and says, "Mike, I can make you $1 million if you could photograph cocktails." And those are intrinsically difficult to photograph. But I spent about a year photographing beers and cocktails, and finally came up with a good collection of images, and we launched into the cocktail collection neckties, and that's where he did make me $1 million. He made me $2 million, as a matter of fact, and that's what we used to actually start this laboratory, to get it off the ground, was the money from the cocktail collection. I grew up in a period when we were in the space race with the Russians, and my parents subscribed to Life magazine. And during my pre-adolescent and adolescent years, I would look at these gorgeous, beautiful photographs of astronauts and spaceships, and the first moon landing happened when I just started college. I was fascinated by the science. Started out as an undergraduate doing synthetic chemistry. I spent 10 years making potential anti-cancer and antiviral agents, just doing straight synthetic chemistry. Then I sort of migrated into biology when I wanted to look at how these drugs candidates that I was making would actually work in live cells. The photography itself through the microscope started out as a hobby for me and became a career as I made money with it and started getting contracts with it. The Silicon Zoo came out of my interest in the early 1990s to basically advance the photography of integrated circuits as an art form. And back in that period of time, I was photographing chips for the chip companies like Intel and Advanced Micro Devices, and they actually form beautiful photographs with nice patterns of the circuitry on the chips, and it gives rise to beautiful color patterns. It looks disorganized, but it's far more organized than it appears, and it really does look like a city from the top. You'll see areas that could be a baseball field, and small areas that could be a series of nestled apartments, things like that. This is a wafer. This is how they're actually made. These chips are all made side by side. So each little square is an individual microprocessor here. So this is an 8-inch wafer, a thin silicon wafer. And so all these chips are made together at the same time in this lithographic process. Then they're sawed up with a diamond saw and then glued into a package. These are collections of my integrated circuits. And so we were doing color photography on these chips, and I stumbled across some things that didn't look right. And the first thing that I stumbled across was appeared to me to be a something to thwart reverse engineering. I spotted this little thing right here, and it didn't look right at first. At first it looked like a little boy with glasses on, and then I realized after photographing it and taking a close look at it that it was a mimic of the character Waldo. I saw that it was actually made into the chip at the time the chip was manufactured. But then, just a few millimeters away on the same chip, I discovered another doodle that looked like Daffy Duck. And that really surprised me. So I started looking at the entire chip, and I found about 15 doodles on this chip. There's a number of other things. Some of them are hidden pretty well. Actually took me quite a while to find everything that's on this chip. The initials of the designers, chip designers, are in here. And they made this chip out in California, and they put a California license plate on it. Right there, you can see that. And this was the R400A chip, so that's the number that's on the license plate. Like I said, this was the first one I ever discovered a doodle on. So I started thinking that maybe these guys are just, just scribbling on these chips. So I started looking at more chips, and I came up with about 15 different doodles, and that's when I built a silicon zoo and put it on the web. And that was back in 1998. So I started getting a lot of emails from people who were actually engineers in this business, and they were informing me of chips that they had done graffiti on and started sending them to me. So within the next couple of years, the collection grew from 15 or 20 to over 300. I have somewhere in here, they come in everything from video cards to microprocessors to cardiac pacemakers. And so what I discovered on these was this graffiti. Well, I was the first one to ever publicize it. I'm not sure that I was the first to discover it. I had no idea that they were doing this. The size of these doodles is quite diverse. Some of them are as large as 2 or 3 millimeters. Some of them are smaller than the width of a human hair. Like, say, for instance, the Crayola crayon is almost 4 millimeters. Waldo is about 30 microns, and the average human hair is about 100 microns in diameter. So 3 Waldos would fit into the cross-section of 1 human hair. And on the surface of the silicon wafer, the engineers deposit a series of layers of aluminum and other materials in order to create the circuitry. They make what we call masks, and those are sort of like a photographic negative. In some cases, it may take 10, 15 masks to make a computer chip, and the doodle may cover 3 or 4 of the masks, so they're actually made up in parts. Eventually, it's actually ultraviolet light that they use to shine through that mask to actually make the chip. So it's a lot more than just drawing a doodle on one particular mask and having it placed onto a chip. The quality of the artwork has gone up since they first started doing it. From the very first doodles that we saw, like the Apollo moon lander on one of the first digital signal processing chips, all the way up to the crayon, the quality of the artwork increased substantially. Many of them had spent 2 or 3 years designing these chips, and so it was sort of their way of signing their artwork, sort of a signature, a way of making it theirs. And if you really look at the vast array of different types of things that these designers have put on the chips, anything from crayons to the space shuttle, there's some pretty spectacular artwork. We found about 350 examples that are in the Silicon Zoo. And we probably searched 10,000 chips. Most chips don't have the doodles on them. It's pretty laborious and tedious looking through the chips. I know of other examples that I don't have copies of. I would say probably a fair estimate is maybe 1,000 to 2,000. Nowadays, as the integrated circuitry shrinks to smaller and smaller sizes, we're seeing far less of them. That's a little hummingbird that we found. That's BIT. Is the name of the company that made it. There's a couple little leaves of some kind there. That's an incredible amount of detail, especially as small as it is. We've talked to a number of the actual designers over the years, and they've told me the origins of their designs, all the way from a dedication to one of their deceased mothers to another one to a lost dog. Girlfriends, scientific advances, a lot of different things have made it onto these chips. The one that I like best was written in Russian on a digital alpha chip, and that was one of the, at that point in time back in the 80s, it was one of the fastest microprocessors in the world. And the engineers from digital had written in Russian, when you steal from digital, you steal the best. So that when Russian scientists decided to reverse engineer this chip, they would read that. That's what the target of that was. I thought that was quite clever. I've never heard of a designer getting fired for this. And like I say, nowadays it's a lot less frequent than it used to be. But I have heard about them getting in trouble for doing it and been told to stop. When they make the chip, there's a lot of people involved in it. And it goes through a number of processes of quality control. And the people that actually make the doodles on the masks are not the last people to look at the chip. They have quality control engineers who will look through there. And those quality control engineers either have to be fooled into not seeing the doodle or in cahoots with the designer to let the doodle pass through the design. And so I think in many cases there was a collaboration to make sure that the doodle actually wound up in the chip. The new Intel chips certainly don't have any doodles on them, and most of the designers are no longer putting them on there.